2.6 Nonlinear Inequalities. This is exercise 1. Solve x minus 5 times x minus 3 is less than or equal to 0. We want to know where this function is less than or equal to 0. This function is equal to 0 at 5 and it's equal to 0 at 3. Now if we multiplied this function out, it's a parabola. It's a parabola whose zeros are at 5 and 3. So 3 and 5, and this parabola is opening up. So this parabola does something like this. Now we want to know where that parabola is less than 0, where the values are negative. In other words, the y values are negative below the x-axis and positive above the x-axis. So just by looking at the graph, we know that this is 0 or negative from 3 to 5. But we're not going to be able to make a graph for every one that we do, so we're going to usually do a number line. So we put where the function would be 0 on the number line, at 3 and at 5. And because of the equals, we can equal 3, we can equal 5. Now we do test points. Maybe I test 0, maybe we test 4, and how about 6? If I plug 0 in here, we have 0 minus 5 and 0 minus 3. Those are both negative, so we have positive values. Well, look, the graph is above the x-axis. The values are positive over here. Now in between 3 and 4, we could test 4. Plug 4 in, we get negative 1. 4 minus 3 is positive 1, but we care more that it's positive. And negative times a positive is a negative. See, the graph is below the x-axis. The y values are negative. Now if we test 6, we get a positive and a positive. That's positive. So again, we see that the values are negative in between 3 and 5. And we can include those values because of the equal. If it just said less than 0, then it would be 3 to 5. We couldn't include 3 or 5. Exercise 2. The first thing we want to do on this is minus 46 from both sides. That way we can compare the left side to 0 instead of comparing it to 46. So we have minus 36 is greater than 0. This factors into x minus 12 and x plus 3. And x cannot equal 12 because we don't have an equal to on the inequality, and x cannot equal negative 3. However, since these are zeros, this is where the function will change signs. So we want to look at these values and test in between. We have negative 3 and we have 12. And we use open dots to indicate that we can't actually use these values. We can't be equal to 0 on this one. So we're going to test negative 4. How about testing 0 and maybe testing 13? So let's test negative 4, and it's easy to plug it into the factored form. So negative 4 minus 12 is negative. Negative 4 plus 3 is also negative, so it's positive. If we throw 0 in, we get negative times a positive, which is negative. And then 13 is a positive and a positive, so that's positive. Well, once again, this is a parabola, so it fits what would happen with the graph, because we'd have negative 3 over here, we'd have 12, and this is what the parabola would look like. So it does go positive, negative, and positive. Now we're looking for positive values and not 0. The positive values are happening from negative infinity to negative 3, but don't include 3. We can't be 0 this time. Union with 12 to infinity. Example 3, we have x to the third minus 3x squared minus 22x plus 24 is greater than 0. Now we can use ending behavior on this because it's a positive x to the third. So with positive x to the third, it probably looks something like this right here. So we know it's going to be negative on the left end and it's going to be positive on the right end. So that might help us. But we need to find the zeros for this function. And the possible zeros are 1, 2, 3, 4, 6, 8, 12, and 24. And of course, we're going to have to test those synthetically. I'm going to fast forward and tell you that this factors into x minus 1, x minus 6, and x plus 4 now has to be greater than or equal to 0. So the zeros are 1, 6, and negative 4. And I wrote can't equal those because we're not allowed to equal 0. So we'll throw those on a number line. To the farthest left is negative 4. Then we have 1, and then we have 6. Now this is a polynomial, and I know that the left side will be negative, and way over on the right will be positive. So now I have to test two values, 0 and maybe 2. So let's plug 0 in. 0 minus 1 is negative. 0 minus 6 is negative. 0 plus 4 is positive. So that's a positive. If I plug 2 in, I get positive, negative, positive. So that's a negative. Now we're looking for the positive values. So the answer is negative 4 to 1, union with 6 to infinity. That's where this function is positive or greater than 0. Number 4, we can add 16 over, so we get 2x to the third minus 12x squared less than or equal to, not less than or equal to, but plus 16x is less than or equal to 0. We can factor out an x, actually a 2x, and get x squared minus 6x plus 8 equals, not equals, less than or equal to 0. We have 2x times x minus 4, x minus 2 less than or equal to 0. And once again, this is an x to the third, but maybe we'll just do the number line with this. So now we can actually equal 0, we can equal 4, and we can equal 2. We are allowed to equal 0. So let's throw these values on a number line. We have 0, 2, and 4, and we can equal these now, so we'll make these solid. And there'll be brackets when we write the interval notation. How about negative 1? How about 1, 3, and 5? So if we throw negative 1 in, we get a negative, and a negative. That's a negative. If we plug 1 in, we get positive. 1 minus 4 is negative. 1 minus 2 is negative. That's going to be positive. Plug a 3 in, positive, negative, positive. That's a negative. And finally, when we throw 5 in, everybody is positive. So that's a positive. Now we want less than or equal to 0, which is negative. So we're looking at negative infinity to 0, and then union with 2 to 4. And that's where the values are negative. Exercise 5, we have polynomial inequalities with unusual solution sets. We cannot factor this one, so maybe we use quadratic formula. Negative 2 plus or minus the square root of b squared minus 4ac divided by 2. And then we get negative 2 plus or minus the square root of 4 minus 12 is negative 8 over 2. So all of the solutions, the only two solutions are imaginary. So this graph does not cross the x-axis. And if you plug in any value, let's say 5, you'd get 25 plus 10 plus 3. That's all positive. So this parabola is above the x-axis and never crosses. So all of the values will be positive. Well, we want all of the values, all the x-coordinates where the y values will be negative. And so there's no solution. That will never happen. Let's look at this one. We got x squared plus 12x plus 36. This one does factor into x plus 6 times x plus 6. And we want to know when is that greater than 0. And so we could write this as x plus 6 squared is greater than 0. So the only 0 is negative 6, but it can't actually equal negative 6. Well, if we look at this graph over here at negative 6, 1, 2, 3, 4, 5, 6, it touches and bounces off because this is counting twice, so it's going to bounce at negative 6. Well, look, all the values are above 0. They're above the x-axis. And we could even show this on a number line. We could have negative 6, open dot, test negative 7, test 0. If we plug negative 7 in, we get negative 7 squared. That's positive. And then if we plug 0 in, 6 squared is positive. Every place is positive except for one value, and that's at negative 6. So the answer is negative infinity to negative 6, union with negative 6 to infinity. So count everything except for negative 6 will be a positive value, greater than 0. Solve a rational inequality. We need to add these two fractions. We have 3x plus 4 over x plus 2 minus 3 times x plus 2 over x plus 2. We need to give this 3 the common denominator. We have 3x plus 4 minus 3x minus 6. That's the top. Now over x plus 2 is less than 0. 3x minus 3x is gone, so we have negative 2 over x plus 2 has to be less than 0. Well, now the only place that this function can change signs is over negative 2. But x cannot be negative 2, but it can change signs over that value. And it cannot be negative 2 because we can't allow the denominator to be 0. So we look at negative 2. We can't allow x to be negative 2, but we can test on either side. So let's test negative 3. So we'd have negative 2 over negative 3 plus 2 when we plug it in. That's a negative over a negative. That's positive. When we plug 0 in, we get negative 2 over 0 plus 2. That's a negative over a positive. That is actually negative. So positive here, negative there. We want the negative values. We want less than 0. So the answer is negative 2 to infinity. Solve x plus 5 over 2x minus 6 is greater than or equal to 1. We compare stuff to 0. We don't compare things to 1. So we're going to minus the 1 over, but give it the common denominator as well. So here is minusing the 1 over and looking at common denominator. Well, we have x minus 2x is negative x. 5 minus negative 6 is plus 11. And that's over 2x minus 6, greater than or equal to 0. So we want to know when is negative x plus 11 equal to 0. You can have the top of a fraction 0. So negative x is equal to negative 11. X is equal to 11. But 2x minus 6 cannot equal 0. We can't allow the denominator to be 0. We have 2x cannot equal 6, and x cannot equal 3. So there's our two values where this function can change signs. So now we're going to put this on a number line. We have 3 and we have 11. And we can not allow this to be 3, but x can be 11. So let's test maybe 0. How about 4 and 12 into the original? Not the original, but actually we'll test it right here. This would be the easiest spot. So if we plug 0 in, we get 11 over negative 6. That's negative. If we plug 4 in, we get negative 4 plus 11. That's positive over 8 minus 6. That's also positive. So positive. Then when we plug 12 in, we get negative 12 plus 11 over 24 minus 6. That's negative over positive. That's negative. We want answers that are greater than or equal to 0, which is positive. So we're looking at 3 to 11. Example 9, solve this one. Well, 6x minus 8 cannot equal 0 because we don't have the equal to part there. But this is where the function can change signs. So we still have to look at this value. So 6x cannot equal 8, x cannot equal 4 over 3, but we have to look at this value as a place where the function can change signs. Also, x cannot equal 6, and x cannot equal negative 1, but we're looking at those values also because the function can change signs over those. Let's throw these on a number line. We got negative 1, we got 4/3, which is 1 1/3. Can't equal, and then we got way out here at 6 can't equal. So let's test negative 2, 0, that's 1 1/3, so 2 is safe, and then test 7. Let's look at negative 2. If we plug negative 2 in to this, we get 12 minus 8, that's positive, over 2 minus 6 is negative, 2 plus 1 is positive, so a positive over a negative is a negative. Plugging 0 in, I get negative over negative times positive. That's negative over negative. That's positive. When we plug 2 in, I get 12 minus 8 is positive. Then I get negative and positive, so that's negative. And plugging 7 in, I get positive, positive, positive. That's a positive. Now we're looking at values that are just greater than 0, which is positive. So the answer is negative 1 to 4/3, and then union with 6 to infinity.